if an electromagnetic waves carry energy, then we might expect them to also carry linear momentum. When an electromagnetic wave encounters the surface of an object, a force that equals dp dt, where the p is the momentum, should be applied. Just when a moving object strikes a surface, it hits the surface with a certain force dp dt. See, this force per unit area exerted by the wave is called radiation pressure. So let's call it capital letter B, not to confuse with the momentum. So I'm going to put a little pressure here, equals force per area. It's known as radiation pressure. So the existence of the radiation pressure was actually predicted by Maxwell. He showed that if a beam of electromagnetic radiation, let's say light for instance, is completely absorbed by an object, then the momentum that is being transferred should equal the energy that is being absorbed by this object in time delta t, and divided by the speed of the electromagnetic wave or speed of light. Well, this is the case. Radiation fully absorbed is fully absorbed. Maxwell also showed that when the radiation is fully reflected, then the radiation momentum that is being transferred is twice as great. So I can say delta P equals 2 times delta U over C, which is the case when we have radiation fully reflected. You might want to ask, what if some of the radiation is absorbed and some of it is reflected? In this case, we can write the transfer of momentum equals some radiation factor A times delta U over C, where this factor A is varying from between 2 and 1. Now, using Newton's second law, force equals dp dt, we can calculate the force and the pressure exerted by the radiation on the object, where the force is given by dp dt and the p is the momentum. So we know that the average rate that is delivered to an object is related to the Poynting vector. So that is a du dt equals Poynting vector average times area. You might want to review my video on electromagnetic waves energy transfer and Poynting vector video. And then come back to this. Then let's continue with our radiation pressure. I can write my the pressure equals force per area, and then here we're gonna assume fully absorbed case. I can say this equals 1 over a dp dt, and for fully absorbed case, the dp should equal du over c, based on our expression right here. So now I can rewrite this expression as 1 over AC du dt. Now we know that this du dt can be represented with the pointing vector right here. So if I substitute this, then we will end up having this equals 1 over AC times pointing vector average. A and A's will cancel out. Then we will have pressure equals S average over the C. And this would be the case when we have radiation fully absorbed. In case of fully reflected, we can say the pressure is twice as great. So the pressure would be 2 times the S average over C. You might be wondering whether you can feel the effects of the radiation pressure on your hand. So usually the radiation from the sun that reaches the Earth's surface transport energy at the rate of 1000 watts per meter square. And so you might want to estimate the pressure of the force that can be exerted by the sun on your outstretched hand. So that would be another an example that I will solve in a separate video. But I want to compare this intensity in terms of lasers. So suppose that you have a very finely focused laser, and this laser is pointed to the atom. And the atoms could be actually irritated by this intensity, and the pressure, radiation pressure, could be dramatic when it is applied to atoms. So an atom has a mass of about 10 to the negative 27 kilogram, in order of 10 to the negative 27 kilogram, and the laser beam can deliver energy that actually could have a big significance on the atoms. And then they can this type of lasers could actually move atoms and molecules around by steering them with the laser beam, and that device is actually called optical tweezers. Optical tweezers. Well, these optical tweezers have some remarkable applications. They are very useful for biologists, and the biologists love those devices, especially since optical tweezers can manipulate live microorganisms and components within a cell without damaging them. That's a very important thing. Optical tweezers have been used to measure the elastic properties of DNA by pulling each end of the molecule with such a laser tweezers. So you might want to read a little bit more on optical tweezers, and there are some simulations on optical tweezers that we could study or examine. But for now, thanks for watching, and stay tuned for more to come. And I will do some example videos later. Thanks.